Hello there, and welcome. Tonight I want to take you somewhere extraordinary, yet profoundly peaceful. Somewhere that exists not just in the vast reaches of space, but in the very fabric of time itself. It's a place where the impossible became possible, where the rules we thought we understood bent gently, like light through water, and where the universe itself took its very first breath. I want to take you to a moment that lasted less than a trillionth of a trillionth of a trillionth of a second, yet shaped everything that would ever be. A moment when space itself expanded faster than light. Not violently, not chaotically, but with a kind of cosmic grace that still echoes in every atom of your being right now as you settle in to listen. Take a deep breath with me. Feel how your chest rises, how the air fills your lungs, how that simple act connects you to everything around you. That breath you just took contains atoms that have been travelling for billions of years, atoms that witnessed the very event we're about to explore together. Some of those oxygen molecules you're breathing right now were forged in the hearts of stars that died before our sun was even born, and those stars themselves emerged from seeds planted in that first impossible moment when the universe expanded faster than the speed of the light. It's a question that might sound alarming at first. How could anything move faster than light, when Einstein told us that was impossible? But what if I told you that this apparent violation of cosmic law was actually the universe's way of creating the perfect conditions for everything that followed, including this very moment where you and I are sharing these thoughts across space and time? Perhaps you're lying in bed right now, the day's worries slowly dissolving as you sink into your pillow. Or maybe you're sitting in a comfortable chair, the room around you growing quiet as evening deepens into night. Wherever you are, whatever time it is in your corner of our spinning world, you're part of this story. And if you're finding comfort in these words, if this journey we're beginning feels like home, I'd love to know where you're listening from. What time is it there? Is it raining perhaps? Or can you see stars through your window? Feel free to share in the comments below, and if this exploration brings you peace, you might consider subscribing so we can take more of these gentle journeys together. There's something beautiful about knowing that people all around our planet are drifting off to these same thoughts, these same wonders, creating a web of quiet contemplation that spans continents and oceans. You see, the story we're about to explore isn't just about abstract physics or distant cosmic events. It's about understanding our place in something magnificent, something that began in a whisper of expansion and continues in every heartbeat, every thought, every dream you've ever had. When we talk about the universe expanding faster than light for that briefest fraction of a second, we're really talking about the moment when possibility itself was born. It was the instant when the cosmos decided that instead of remaining an infinitesimally small point of infinite density, it would become something vast and beautiful, something with room for galaxies and gardens, for black holes and butterflies, for questions and for questioners like us. Consider this for a moment. The entire observable universe, everything we can see with our most powerful telescopes, every galaxy containing hundreds of billions of stars, all of it was once smaller than a single proton. Smaller than the smallest thing we can measure, smaller than the quantum foam that bubbles at the tiniest scales of reality. And then, in a moment so brief that we don't even have proper words for its duration, space itself began to stretch. Not objects moving through space, but space itself expanding, carrying everything with it like raisins in rising bread dough, except infinitely faster, infinitely more gentle, infinitely more precise. This expansion, which cosmologists call inflation, might seem like it should have been violent, chaotic, a cosmic explosion of unimaginable force. But what if it wasn't? What if this faster-than-light expansion was actually the universe's way of becoming smooth and peaceful, like a wrinkled sheet being gently pulled taut? What if that impossible speed was necessary to create the serene cosmos we inhabit today, where galaxies drift like islands in a calm sea, where stars burn steadily for billions of years, where planets can orbit in stable paths that allow for the slow emergence of life and consciousness? The mathematics tell us something remarkable. Without this brief period of faster-than-light expansion, the universe would be a very different place. Perhaps it would be too lumpy, with matter clumped together in ways that would never allow for the formation of stars, or perhaps it would be too smooth, with no variations at all to seed the cosmic structures we see today. But inflation, This moment of impossible speed created exactly the right conditions. It's as if the universe knew what it needed to become and took that first expansive breath with perfect precision. Think about water for a moment. When you pour water into a glass, it might splash and swirl, creating temporary chaos. But if you wait, if you're patient, the water settles. It becomes perfectly level, perfectly calm. Now imagine if you could speed up that settling process, make it happen almost instantaneously. That's somewhat like what inflation did for the early universe. It took what could have been a chaotic, turbulent beginning and smoothed it out in less time than it takes light to cross the smallest measurable distance. And here's where it gets even more wondrous. During this inflation, tiny quantum fluctuations, the smallest possible ripples in the fabric of space-time, were stretched to cosmic scales. These infinitesimal variations, smaller than anything we can directly measure, became the seeds for everything we see in the universe today. Every galaxy cluster, every cosmic void, every strand in the vast web of matter that spans billions of light years, all of it traces back to quantum whispers that were amplified during that moment of faster-than-light expansion. Scientists have actually measured the afterglow of this event. When you tune an old television to a channel with no signal, about 1% of that static you see is actually radiation left over from the early universe. We call it the cosmic microwave background, and it's like a baby photo of the cosmos, taken when it was only 380,000 years old. In that photo, we can see the faint imprints of those quantum fluctuations, stretched and preserved like fossilized ripples on an ancient beach. The pattern is almost perfectly uniform, varying by only about 1 part in 100,000, which tells us just how smoothly and evenly inflation worked its magic. But why faster than light? How could space itself expand faster than the ultimate cosmic speed limit? The answer lies in understanding what Einstein's speed limit actually means. Nothing can travel through space faster than light. That's true. But space itself isn't traveling through anything. It's simply expanding, creating more of itself. Imagine drawing 2 dots on a balloon and then inflating it. The dots move apart, but they're not moving through the balloon's surface. The surface itself is expanding, carrying the dots with it. During inflation, space expanded so rapidly that points in the universe moved apart faster than light could travel between them, yet nothing actually exceeded the speed of light in its local environment. This distinction might seem like cosmic hair-splitting, but it's crucial to understanding how our universe could have become so large and so uniform. Light, even given billions of years, couldn't have traveled from one edge of the observable universe to the other to even out temperatures and densities. Yet everywhere we look, in every direction, the universe looks remarkably the same. The cosmic microwave background has almost exactly the same temperature, whether we look north or south, east or west, toward the constellation of Virgo or toward the constellation of Aquarius. This uniformity is called the horizon problem, and inflation solves it elegantly. Before inflation, all these regions were close enough to communicate and come to equilibrium. Then inflation stretched them far apart, preserving that uniformity across vast distances. There's something deeply calming about this idea, isn't there? The universe didn't begin in chaos that slowly organized itself. Instead, it began with a kind of cosmic decision to be smooth, to be even, to create a space where complexity could slowly emerge, without being overwhelmed by turbulence. It's as if the cosmos knew that for stars to form, for planets to coalesce, for life to eventually emerge, it needed to start with a canvas that was neither too rough nor too perfectly blank. Let me share something that might help you visualize this better. Imagine you're floating in a vast, warm ocean at night. The water is so calm that you can't tell where it ends and the starry sky begins. Now imagine that ocean suddenly, gently, expanding in all directions. Not violently, not with waves or turbulence, but smoothly, evenly, like the universe itself is taking a deep, peaceful breath. You're not thrown about by this expansion. Instead, you find yourself in an even vaster, even calmer ocean, with more room to float, more space to exist, more possibilities for what might emerge from those quiet waters. This is what inflation gave us, not just space, but spaciousness. Not just room for matter, but room for meaning. The faster-than-light expansion wasn't a violation of cosmic law, but a fulfillment of cosmic potential. It was the universe's way of saying, I choose to be vast, I choose to be smooth. I choose to create conditions where complexity can emerge, where consciousness can eventually arise to contemplate its own origins, and contemplate we do. Here we are, made of atoms forged in stars, arranged in patterns complex enough to wonder about our own existence, looking back across billions of years to understand that first moment of expansion. We're able to do this because inflation created a universe stable enough for stars to burn steadily, for planets to orbit reliably, for chemistry to work the same way everywhere, for physics to be dependable and discoverable. The numbers involved are almost beyond comprehension, yet they have a poetry to them. During inflation, the universe expanded by a factor of at least 10^26. That's a 1 followed by 26 zeros. To put that in perspective, if you enlarged a single proton by that factor, it would become larger than our entire solar system, and this happened in about 10^32 seconds. That's a decimal point followed by 31 zeros and then a 1. These numbers are so extreme they almost cease to have meaning, yet they describe something that definitely happened, something that left its fingerprints all over the cosmos we observe today. What strikes me most about inflation is how it transformed potential into actuality. Before inflation, the universe contained all the energy and matter that would ever exist, but compressed into an impossibly small space. There was no room for structure, no space for stories, no time for processes to unfold. Inflation changed that. It took that dense seed of potential and gave it room to breathe, room to become, room to evolve into something magnificent. Think about a seed for a moment. A tiny acorn contains all the information needed to become a mighty oak tree, but it needs space to grow, soil to expand into, room for its branches to spread. Inflation was like the universe planting itself in the soil of space-time, giving itself the room it needed to grow into the cosmic forest we see today. And just as a forest is more than just trees, it's also the spaces between them, the air that flows through them, the light that filters down to the forest floor. The universe is more than just matter and energy. It's also the vast spaces between galaxies, the cosmic voids that give structure to the whole, the dark expanses that make the bright spots meaningful. This perspective transforms how we might think about emptiness. The vast stretches of apparently empty space aren't absences or voids in any negative sense. They're the result of that primordial expansion, the breathing room that inflation created. Every cubic meter of seemingly empty space is actually teeming with virtual particles popping in and out of existence, with fields that carry forces, with the expanding fabric of space-time itself. What we call emptiness is actually fullness at a scale we're only beginning to understand, and perhaps this is why the idea of faster-than-light expansion doesn't disturb our sense of cosmic order, but actually reinforces it. The universe needed to break its own future rules to create a space where those rules could apply. It's like a painter who needs to prepare a canvas before the actual painting can begin. The canvas preparation doesn't follow the same rules as the painting itself, but without it, there would be nowhere for the art to exist. As you lie there listening, perhaps you can feel yourself as part of this vast, expanded space. Your body, made of atoms that were once compressed in that primordial seed, now spread out in the pattern we call you. The calcium in your bones, the iron in your blood, the oxygen you're breathing, all of it was there in the beginning, waiting for inflation to give it room to become. You are not separate from the universe's story. You are a chapter in it, written in atoms and molecules, in thoughts and dreams. The questions that inflation raises are as fascinating as the answers it provides. Did inflation happen just once, or does it happen over and over in different regions, creating a multiverse of pocket universes, each with its own laws of physics? Is our universe just one bubble in an infinite foam of inflating space-time? These aren't just wild speculations. They're serious scientific hypotheses that follow naturally from our understanding of how inflation works. You see, once inflation starts, it's hard to make it stop everywhere at once. Quantum mechanics tells us that different regions might stop inflating at different times, like bubbles forming in boiling water. Our observable universe might be just one such bubble, one region where inflation ended and the energy of expansion converted into the matter and radiation we see today. Beyond our cosmic horizon, inflation might still be happening, creating new universes, new spaces for possibility. This idea of eternal inflation is both humbling and oddly comforting. It means our universe, vast as it is, might be just one note in an infinite symphony, one story in an endless library. It doesn't diminish our importance. If anything, it makes our existence even more precious. In an infinite multiverse, the fact that we're here, conscious and wondering, becomes even more wonderful. We're not just lucky to exist in a universe. We're lucky to exist in a universe that allows us to contemplate the existence of other universes. But let's return to our universe, to the one we know and can observe. The evidence for inflation is written across the sky in multiple languages. There's the uniformity of the cosmic microwave background, which we've already discussed. But there's also the flatness of space itself. When we measure the geometry of the universe on the largest scales, we find that it's flat to an extraordinary precision. Parallel lines remain parallel even across billions of light years. The angles of enormous triangles drawn between distant galaxies add up to exactly 180 degrees, just as they would on a flat piece of paper. This flatness is another gift from inflation. Without it, space might have been curved like the surface of a sphere or saddle-shaped like a Pringles chip. Either of these geometries would have led to a very different cosmic evolution. A spherical universe would have eventually collapsed back on itself. A saddle-shaped universe would have expanded so quickly that matter could never have clumped together to form stars and galaxies. But inflation stretched space so much that any initial curvature was flattened out, like stretching a curved rubber sheet until it becomes perfectly flat. The precision of this flattening is remarkable. Observations tell us that the universe is flat to within 0.4% accuracy. That's like having a billiard table the size of Earth that varies in height by less than a centimetre. This kind of precision doesn't happen by accident. It's the signature of a process that smoothed and flattened space on the grandest possible scale. There's also the mystery of magnetic monopoles. According to many theories of particle physics, the extreme conditions of the very early universe should have produced magnetic monopoles. Particles with only a north or south magnetic pole, not both. These particles should be abundant, yet we've never detected a single one. Inflation solves this puzzle elegantly. If monopoles were created before inflation, they would have been diluted to undetectable densities by the rapid expansion, like a drop of ink dispersed in an ocean. Each piece of evidence for inflation is like a note in a cosmic chord, and when played together, they create a harmonious picture of our universe's beginning. The flatness, the uniformity, the absence of monopoles, the pattern of fluctuations in the cosmic microwave background, all of these observations point to the same conclusion. Our universe underwent a brief period of exponential expansion that set the stage for everything that followed. But what caused inflation? What was the field or force that drove this rapid expansion? Physicists call it the inflaton field, and while we don't yet know exactly what it was, we can describe its properties. It must have been a field with very special characteristics, smooth, uniform, and carrying an enormous amount of energy. As this field rolled down its potential energy curve, like a ball rolling down a gentle hill, it drove the expansion of space. When it reached the bottom of the hill, inflation ended, and the field's energy converted into the particles and radiation that filled the young universe. This process, called reheating, was when the universe as we know it truly began. The energy that had been driving expansion suddenly became available for other purposes. It condensed into quarks and leptons, the building blocks of matter. It became photons, the particles of light. It became the dark matter whose gravity would later pull ordinary matter into the first stars and galaxies. In a very real sense, everything we see around us is the transformed energy of that primordial inflation field. The temperature at the end of inflation was enormous, perhaps 1027 degrees, far hotter than the centre of any star that exists today. Yet this hellish heat was necessary for the universe to begin its long journey toward complexity. As the universe continued to expand and cool, those first particles began to combine. Quarks joined to form protons and neutrons. These joined to form the first atomic nuclei. And after 380,000 years of cooling, electrons finally joined with nuclei to form the first atoms, and the universe became transparent to light for the first time. It's worth pausing here to appreciate the profound connection between that first moment of inflation and this moment right now. The device you're using to listen to these words contains electrons that have been travelling through the universe for over 13 billion years. The photons illuminating your room, whether from a lamp or from the sun filtered through your window, are following the same laws of physics that were established when inflation ended. The gravity holding you to Earth is the same force that pulled the first galaxies together from those tiny quantum fluctuations stretched across the sky. We are not separate from this story. We are its continuation. Every thought you think is possible because inflation created a universe where complexity could emerge. Every feeling you feel is enabled by the stable laws of physics that crystallized when inflation ended. Every dream you dream takes place in a brain made of atoms that were given room to exist by that first exponential expansion. As we prepare to dive deeper into this cosmic mystery, to explore how we've come to understand inflation and what it means for our future, take a moment to appreciate where we are. We're 13.8 billion years into a story that began with the universe expanding faster than light. We're conscious arrangements of matter that can look back and understand our own origins. We're the universe's way of contemplating itself, of wondering about its own beginning. The night sky, if you can see it from where you are, is both a window into the past and a mirror of our present. Those stars you might see are not just distant suns, but time machines, showing us light that left them years, decades, or centuries ago. And beyond them, invisible to our eyes but visible to our telescopes, are galaxies whose light has been travelling since the universe was young. Further still, in every direction, is that faint microwave glow, the cooled remnant of the universe's first light, still carrying the imprint of inflation's quantum fluctuations. In our next movement through this cosmic story, we'll explore how we can compress these vast timescales into something our minds can grasp, how we can take billions of years and fold them into a single day that we can understand. We'll see how your life, brief as it might seem, is actually a significant part of the universe's story, how the atoms in your body have been on an incredible journey that began with inflation and continues with every breath you take. But for now, as this first part of our journey comes to a gentle pause, let yourself feel the profound peace of being part of something so vast yet so intimate. The universe expanded faster than light to create room for you to exist. It smoothed itself out so that stars could form to forge the elements you're made of. It preserved tiny quantum fluctuations so that galaxies could form, including the one we call home. Every impossible thing about that first fraction of a second was necessary for this moment, for you lying there listening, for us sharing this wonder across space and time. The expansion continues, of course. Space is still stretching, carrying galaxies away from each other like boats on an expanding sea. But it's gentle now, patient, giving us billions of years to evolve, to learn, to discover our own story. The violence and chaos that could have been was smoothed away by inflation, leaving us in a cosmos that's vast and mysterious. Yes, but also stable and knowable, a place where consciousness can emerge and flourish. As you drift deeper into rest, remember that you're not just in the universe, you are the universe, a pattern of atoms and energy that has temporarily arranged itself into the miracle of you. The faster-than-light expansion that seems so alien, so impossible, is actually the reason you're possible. It's the cosmic inhale that preceded the long, slow exhale we're all part of now. Now, let's journey together into the second movement of our cosmic story, where we'll take these incomprehensible billions of years and transform them into something as familiar as a single day. Imagine if we could compress all of cosmic history, from that first moment of inflation to right now, into just 24 hours. Where would we be in that day? When would the Earth form? When would life begin? When would consciousness emerge to contemplate its own existence? The answers might surprise you with both how brief our moment is and how perfectly timed our arrival has been. If we compress the entire 13.8 billion year history of the universe into a single day, inflation happened in a period so brief that we don't have words small enough to describe it. It would be like trying to identify a moment shorter than the smallest fraction of time we can conceive. The entire period of inflation, that faster-than-light expansion that set everything in motion, would have occurred in the first incomprehensibly tiny fraction of the first second after midnight. By the time the cosmic clock had ticked even 1 second, inflation was long over, and the universe had already begun its more sedate expansion that continues today. In this cosmic day, the first atoms wouldn't form until about 10 minutes after midnight. For 10 minutes of our compressed day, the universe was too hot for even atoms to exist. It was a soup of free particles, a plasma of unbound protons, neutrons, and electrons, along with countless photons of light that couldn't travel far before colliding with something. Imagine trying to see through a fog so thick that light can only travel a few inches before being absorbed or scattered. That was the entire universe for the first 380,000 years, or about 20 minutes of our cosmic day. When the universe finally became transparent to light, when those first atoms formed and photons could travel freely, it was still just 20 minutes past midnight in our compressed timeline. The cosmic microwave background that we observe today, that baby picture of the universe, was taken at 12:20 a.m. Everything else, all the stars, all the galaxies, all the planets, all of life, happened in the remaining 23 hours and 40 minutes of this single cosmic day. The first stars didn't begin to shine until about 1 a.m. For 40 minutes of our cosmic day, the universe was completely dark except for the fading glow of the Big Bang itself. This period, which astronomers call the cosmic dark ages, lasted for hundreds of millions of actual years. It was a time of quiet preparation, as gravity slowly, patiently pulled matter together into the clumps that would eventually ignite as the first stars. These weren't like the stars we see today. They were massive, perhaps hundreds of times the mass of our Sun, and they burned bright and died young, lasting only a few million years before exploding as supernovae. These first stellar explosions were crucial for our existence. The Big Bang produced only hydrogen, helium, and tiny traces of lithium. Everything else, the carbon in your cells, the oxygen you breathe, the iron in your blood, the calcium in your bones, all of these elements were forged in the nuclear furnaces of stars or in the violent explosions of their deaths. When the first stars died, they seeded space with these heavier elements, making possible the formation of rocky planets and, eventually, life itself. By 2:00 a.m. in our cosmic day, galaxies were beginning to form in earnest. These weren't the beautiful spiral and elliptical galaxies we see today, but smaller, irregular collections of stars that would later merge and combine to form larger structures. The universe was becoming increasingly complex, with matter organizing itself into hierarchical structures, stars within galaxies, galaxies within clusters, clusters within superclusters, all connected by vast filaments of dark matter and ordinary matter that create the cosmic web we observe today. Our own Milky Way galaxy began to form around 3:00 a.m. Though it looked nothing like the beautiful spiral galaxy we inhabit today. It was smaller, more chaotic, growing by consuming smaller galaxies and accumulating gas from its surroundings. The supermassive black hole at its centre, which today has a mass equal to 4 million suns, was already beginning to form, though we still don't fully understand how these cosmic monsters grew so large so quickly. As our cosmic day progresses through the morning hours, the universe continues its patient work of building complexity. Stars are born and die, each generation enriching the cosmic gas with heavier elements. Galaxies collide and merge, triggering bursts of star formation. Black holes grow by consuming matter and merging with other black holes. The universe is becoming more diverse, more structured, more capable of supporting the complex chemistry that will eventually lead to life. It's not until 3:36 p.m., more than 15 hours into our cosmic day, that our own sun begins to form. The universe has already lived through more than 9 billion years of actual time before our solar system even begins to coalesce from a cloud of gas and dust, enriched by generations of previous stars. This cloud, which astronomers call the solar nebula, was probably triggered to collapse by the shockwave from a nearby supernova, the death of a massive star providing the push needed for new stars to be born. The Earth forms at 3:50 p.m., just 14 minutes after the Sun in our compressed timeline. For the first few million years, our planet is a hellish place, bombarded by asteroids and comets, its surface molten from the heat of countless impacts. The Moon forms during this violent period, probably the result of a Mars-sized object colliding with the young Earth and throwing debris into orbit. By 4:00 p.m., the worst of the bombardment is over, and Earth begins to cool and solidify. Life appears surprisingly quickly in our cosmic day. By 4:30 p.m., just 40 minutes after Earth formed, the first primitive life has already emerged. We don't know exactly how life began, whether it formed in warm pools on Earth's surface, in deep-sea hydrothermal vents, or perhaps even arrived from space on meteorites. But we do know that by 3.8 billion years ago, or 4:30 p.m. in our compressed day, life had taken hold on our planet. For the next 7 hours of our cosmic day, life remains microscopic and relatively simple. Bacteria and archaea dominate the planet, slowly transforming its atmosphere and oceans. Around 8:30 p.m., a revolutionary event occurs. Photosynthesis evolves, allowing life to harness energy directly from sunlight. This innovation will eventually transform Earth's atmosphere, filling it with oxygen and making possible the emergence of more complex forms of life. But that transformation takes time. It's not until 10th p.m. that oxygen levels in the atmosphere rise significantly, an event known as the Great Oxidation Event. This is actually a catastrophe for most existing life, which had evolved in an oxygen-free environment. The oxygen is poison to these anaerobic organisms, causing perhaps the first mass extinction in Earth's history. But it also sets the stage for new forms of life that can use oxygen for energy, a much more efficient process than anaerobic metabolism. Complex cells with nuclei, eukaryotes, don't appear until about 10:30 p.m. These cells, which will eventually give rise to all plants, animals and fungi, are probably the result of one cell engulfing another in a process called endosymbiosis. The engulfed cells become mitochondria, the powerhouses that provide energy for all complex life. This is such an unlikely event that it may have happened only once in Earth's entire history, making all complex life on Earth descendants of that single cellular merger. Multicellular life doesn't appear until 11:00 p.m. For most of Earth's history, for most of our cosmic day, life consisted only of single cells. The emergence of multicellularity, of cells working together as a single organism, is another revolutionary innovation that transforms the possibilities for life. But even then, these early multicellular organisms are simple, soft-bodied creatures that leave few fossils for us to study. The Cambrian explosion, when complex animal life suddenly diversifies into many of the major groups we see today, doesn't occur until 11:40 p.m. In just a few minutes of our cosmic day, corresponding to a few tens of millions of years of actual time, life invents eyes, shells, spines, and countless other innovations. The oceans fill with strange and wonderful creatures, many of which have no modern descendants. Plants don't colonize land until 11:45 p.m. For almost the entire cosmic day, the continents have been barren rock, sculpted only by wind and water. But once plants establish themselves on land, they begin transforming the landscape, breaking down rock into soil, providing food and shelter for the animals that will soon follow them out of the oceans. Dinosaurs don't appear until 11:52 p.m., just 8 minutes before midnight in our cosmic day. They dominate the planet for what seems like an eternity to us, over 150 million years. But in our compressed timeline, their entire reign lasts only about 4 minutes. The asteroid that ends their dominance strikes at 11:56 p.m., clearing the way for mammals to diversify and eventually produce us. Our earliest human ancestors don't appear until 20 seconds before midnight. The entire history of humanity, from our first upright walking ancestors to now, occupies only the last 20 seconds of the cosmic day. Modern humans, Homo sapiens, don't appear until the last fifth of a second. All of recorded human history, every civilization, every empire, every work of art, every scientific discovery, every person who has ever lived and loved and wondered about their place in the universe, all of it happens in the last few thousandths of a second before midnight. In the final millisecond of our cosmic day, humans develop agriculture, build cities, invent writing, discover that Earth orbits the Sun, realize that the Sun is just one star among billions, discover that our galaxy is just one among billions, and figure out that the universe began with a period of faster-than-light expansion called inflation. In less than the blink of an eye on the cosmic scale, we go from cave paintings to sending spacecraft to other planets, from wondering what the lights in the sky might be, to measuring the cosmic microwave background with exquisite precision. This perspective might make us feel insignificant, like cosmic latecomers to a party that's been going on for hours, but consider this. We arrive at exactly the right time. If we had emerged much earlier in the cosmic day, we wouldn't have been able to see the evidence for inflation. The cosmic microwave background would have been too hot to detect, with the kind of technology a young civilization could develop. The universe would have been denser, more chaotic, with more frequent catastrophic events like supernova and galaxy collisions. And if we had arrived much later? The accelerating expansion of the universe means that galaxies are moving away from each other faster and faster. In the far future, perhaps around 2 sequaem of the next cosmic day, galaxies outside our local group will have moved beyond our cosmic horizon. Future civilizations will look out and see only our own galaxy and a few nearby companions, with no evidence of the billions of galaxies we can see today. They might never discover the Big Bang, never learn about inflation, never realize the true scale and history of the universe. We exist in a golden window of cosmic time, when the universe is old enough to have produced the complexity necessary for consciousness, but young enough that we can still see and understand our origins. We can detect the cosmic microwave background, observe distant galaxies, measure the expansion of space, and piece together the story of inflation. We are the universe's memory, its way of remembering and understanding its own beginning. Think about what this means for your own existence. Every atom in your body, except for hydrogen, was forged in the heart of a star that died before our sun was born. You're made of cosmic recycling, of matter that has been part of other stars, other planets, perhaps even other living beings on worlds we'll never know about. The carbon in your DNA, the iron in your blood, the calcium in your bones, all of it has been on an incredible journey through space and time to arrive here, now, arranged in the pattern that is you. And it's not just the matter you're made of that connects you to the cosmic story. The very forces that hold you together, the electromagnetic force that bonds your atoms into molecules, the strong force that holds atomic nuclei together, the weak force that allows the sun to shine, and gravity that keeps you grounded on Earth. All of these forces emerged in the first fraction of a second after inflation ended. They've been operating unchanged for 13.8 billion years, and they operate the same way in your body as they do in the most distant galaxy we can observe. Your consciousness itself is a cosmic phenomenon. The electrical impulses in your brain follow the same laws of physics that govern lightning on Jupiter and magnetic fields around black holes. The quantum mechanics that describes the behavior of neurotransmitters in your synapses is the same quantum mechanics that created the fluctuations during inflation that seeded all cosmic structure. When you think a thought, you're using the same fundamental processes that the universe has been using since the beginning of time. This is why the story of inflation matters, why understanding that the universe expanded faster than light for a fraction of a second isn't just abstract physics, but deeply personal history. That moment of impossible expansion created the conditions for your existence. It smoothed out the universe so that stable structures could form. It amplified quantum fluctuations into the seeds of galaxies. It set in motion the chain of events that would lead, 13.8 billion years later, to you lying here, listening to this story, being part of this story. As we move through our cosmic day, we can see how each moment builds on the last, how each innovation makes the next one possible. Inflation makes possible the formation of atoms. Atoms make possible the formation of stars. Stars make possible the creation of heavy elements. Heavy elements make possible the formation of rocky planets. Rocky planets make possible the emergence of life. Life makes possible the evolution of consciousness. And consciousness makes possible the understanding of inflation itself. It's a beautiful circle, isn't it? The universe begins with an impossible moment of faster than light. Expansion evolves for billions of years, and eventually produces beings capable of discovering and understanding that first impossible moment. We are the universe's way of comprehending its own origin, of closing the loop between beginning and understanding. But our cosmic day isn't over. It's still a few minutes before midnight, and those few minutes represent millions of years of future time. What will happen in those remaining minutes? Will humanity spread to other planets, other star systems? Will we discover other life in the universe? Will we finally understand the nature of dark matter and dark energy? Will we discover that inflation is still happening somewhere beyond our cosmic horizon, creating new universes we can never observe? These questions remind us that we're not just passive observers of the cosmic story. We're active participants, capable of shaping what happens in our corner of the universe. Every choice you make, every action you take becomes part of the cosmic story. When you learn something new, the universe becomes a little more self-aware. When you create something beautiful, you add to the complexity and wonder that inflation made possible. When you connect with another person, you're participating in the most complex phenomenon we know of, the interaction of conscious beings. The compression of cosmic time into a single day also helps us understand the preciousness of our moment, We exist in a tiny sliver of cosmic time, a fraction of a second in the cosmic day. Yet this fraction contains all of human history, all of human achievement, all of human potential. Every human life, lasting perhaps 80 or 90 years, represents only a few microseconds of the cosmic day. Yet in those microseconds, a person can love, create, discover, and contribute to the ongoing story of the universe. This perspective transforms how we might think about our daily concerns and worries. That problem that's keeping you awake? In the context of the cosmic day, it exists for less time than it takes a photon to cross an atom. Yet it's also true that your experience of that problem, your consciousness of it, is one of the most complex phenomena in the universe. Your matter contemplating itself, time aware of its own passing, space conscious of its own extent. As our cosmic day moves through its final minutes toward midnight, we can see acceleration in the pace of change. For most of the day, change was slow, patient, measured in millions or billions of years. But as we approach midnight, the pace quickens, life diversifies explosively, intelligence emerges, technology develops. We go from stone tools to space telescopes in what amounts to a cosmic eye blink. This acceleration might continue. Some scientists speculate that we're approaching a technological singularity, a point where artificial intelligence surpasses human intelligence and begins improving itself at an exponential rate. If this happens, it might occur in the next few microseconds of our cosmic day. The universe might be about to become conscious of itself in ways we can barely imagine. Or perhaps consciousness like ours is rare, precious, and fragile. Perhaps we're one of the few places in the universe where matter has organized itself into patterns complex enough to contemplate their own existence. In that case, our responsibility is even greater. We're not just preserving our own species, we're preserving the universe's ability to know itself, to remember its beginning, to wonder about its future. The cosmic day metaphor also helps us understand our relationship with time itself. We experience time as a flow from past to future, as something we move through. But physics tells us that time is more like a dimension, like space. All moments exist simultaneously in the block universe of space-time. The moment of inflation still exists, frozen in the structure of space-time, just as this moment exists, just as all future moments already exist. From this perspective, nothing is ever truly lost. Every moment of the cosmic day, from the first fraction of a second to right now, exists eternally in space-time. Your life, brief as it might seem on the cosmic scale, creates a permanent pattern in the fabric of the universe. Every joy you experience, every connection you make, every moment of wonder you feel, becomes part of the eternal structure of space-time. This is perhaps the deepest gift of understanding cosmic time. The realization that our brevity doesn't diminish our significance. Yes, we exist for only a tiny fraction of the cosmic day, but that fraction is essential. Without consciousness arising to observe and understand the universe, all those billions of years of cosmic evolution would be like a tree falling in a forest with no one to hear it. We provide the universe with witnesses, with appreciators, with beings capable of awe and wonder. As we prepare to explore the actual mechanism of inflation, to understand how space itself could expand faster than light without violating the laws of physics, carry with you this sense of your place in cosmic time. You're not separate from the story of the universe, you're its current chapter. You exist at the perfect moment to understand your origins and contemplate your future. You're made of ancient stardust, held together by forces that emerged in the first instant of time, conscious through processes that represent the highest complexity the universe has achieved. The cosmic day continues and we're part of its unfolding. Every breath you take, every thought you think, every dream you dream adds to the richness of the universe's story. You're not just in the universe, you are the universe, experiencing itself subjectively, contemplating itself consciously, understanding itself scientifically. In this vast sweep of time, from the first impossible moment of inflation to the present, we see not chaos but order, not randomness but pattern, not isolation but connection. Everything is connected to everything else through the shared history of our cosmic day. The atoms in your right hand might have come from a different star than the atoms in your left hand, but they all trace back to the same moment of inflation, the same impossible beginning that made everything possible. Now, as we've seen our place in the cosmic timeline, as we've compressed billions of years into a single day, and found ourselves in the last fraction of a second before midnight, we're ready to explore the mechanism itself. How exactly did space expand faster than light? What does it mean for space itself to stretch? How can we reconcile this with Einstein's speed limit? The answers will take us into the very fabric of reality, into the quantum foam that underlies all existence, into the fields that permeate every point in space and time. The story of how space expanded faster than light is not just a story of the past. The expansion continues, accelerating even now, carrying galaxies away from each other at ever-increasing speeds. In some sense, we're still inside that primordial expansion, still riding the wave that began in the first fraction of a second. Understanding how it works, how space itself can stretch and carry us along, will deepen our appreciation for the cosmic dance we're all part of, the eternal expansion that gave us room to exist and continues to give us room to grow. Let me take you now into the heart of this mystery, into the mechanism of expansion itself, where we'll discover that the impossible is not only possible but necessary, not only necessary but beautiful, not only beautiful but continuing all around us, in every cubic centimetre of space, in every moment of time, in every atom of our beings. The question seems to defy everything we think we know about the universe. How can anything travel faster than light when Einstein showed us that the speed of light is the ultimate cosmic speed limit? The answer lies in understanding what actually happened during inflation, and it's more subtle and more wonderful than you might imagine. Nothing actually travelled faster than light. Instead, space itself expanded, and there's no limit to how fast space can expand because space isn't travelling through anything. It's simply creating more of itself. Imagine you're standing on a vast rubber sheet with a friend standing a few feet away. Now imagine that rubber sheet begins to stretch uniformly in all directions. You and your friend haven't moved. You're both standing perfectly still on the sheet, yet you're getting farther apart because the sheet itself is expanding between you. If the sheet stretches fast enough, you could be moving apart faster than you could ever run toward each other, even though neither of you is actually running. This is essentially what happened during inflation, except instead of a two-dimensional sheet, it was the three-dimensional fabric of space itself that was stretching. But even this analogy doesn't quite capture the strangeness of what happened. The rubber sheet is expanding into something, the room around it perhaps, but space isn't expanding into anything. There's no outside of space for it to expand into. Instead, space is simply creating more of itself internally. Every point in space is moving away from every other point, not because they're travelling through space, but because more space is appearing between them. Think of it this way. Imagine you have a loaf of raisin bread dough that's rising. As the dough expands, the raisins move apart from each other. From the perspective of any individual raisin, all the other raisins are moving away from it. The farther away another raisin is, the faster it appears to be receding, yet no raisin is actually moving through the dough. The dough itself is expanding, carrying the raisins along for the ride. During inflation, we were all raisins in the cosmic dough, and the dough was expanding at an incredible rate. This distinction between motion through space and the expansion of space itself is crucial. Einstein's special relativity tells us that nothing can travel through space faster than light. This speed limit is built into the very structure of space-time. It's not just a rule, it's a fundamental aspect of how cause and effect work in our universe. If something could travel faster than light through space, it could arrive at its destination before it left its origin, creating paradoxes that would unravel the logical structure of reality. But the expansion of space doesn't create these paradoxes. When space expands between two objects, neither object is actually moving through space at all. They're at rest in their local environment, even as that environment is being carried along by the expansion. It's like sitting still in a boat on a river. You're not moving relative to the boat, but the current is carrying you downstream. During inflation, the current was the expansion of space itself, and it was flowing incredibly fast. The mathematics of this expansion is described by something called the scale factor. Imagine that at any moment we assign a number to the universe that describes its size. During normal times, this number increases slowly. During inflation, it increased exponentially. Every tiny fraction of a second, the universe doubled in size, then doubled again, then again. This doubling happened at least 80 times during inflation, possibly many more. Each doubling took only about 10 las or 35 seconds, a time so short that light could travel only the smallest possible distance quantum mechanics allows. To understand how dramatic this expansion was, let's put it in perspective. If you started with something the size of a proton and doubled it 80 times, it would end up larger than the entire observable universe today. That's the minimum expansion that occurred during inflation. The actual expansion might have been much greater, and all of this happened in less time than it takes light to cross the nucleus of an atom. But here's where it gets even more interesting. This expansion wasn't driven by any kind of explosion or force pushing things apart. Instead, it was driven by the energy of empty space itself. You see, quantum mechanics tells us that empty space isn't really empty. It's filled with fields, the electromagnetic field, the electron field, the quark fields, and many others. Even when these fields are in their lowest energy state, they still have some energy, called zero-point energy or vacuum energy. During inflation, there was an additional field, which physicists call the inflaton field. This field was stuck in what's called a false vacuum state. Imagine a ball sitting in a valley on a hillside. The valley isn't the lowest point, that would be the base of the hill, but the ball is temporarily stable there. The inflaton field was like that ball, stuck in a temporary valley of potential energy. And while it was stuck there, its energy density remained constant even as space expanded. This is the key to understanding inflation. Normally, when something expands, its energy density decreases. If you have a box of gas and you make the box bigger, the gas becomes less dense. But during inflation, the energy density of the inflaton field stayed constant as space expanded. This meant that the total energy in the universe was increasing. More space with the same energy density means more total energy. This energy drove further expansion, which created more space, which contained more energy, which drove more expansion in an exponential feedback loop. It's as if you had a magical substance that, when you stretched it, didn't become thinner but instead created more of itself to maintain the same thickness. The more you stretched it, the more of it there would be, providing more material to stretch, creating even more material. This is what space did during inflation, except the material was the energy of the inflaton field, and the stretching was the expansion of space itself. This process might sound like it violates the conservation of energy, one of the most fundamental principles in physics. How can the total energy of the universe increase? The answer is that gravity has negative energy. As the universe expanded and created more positive energy in the inflaton field, it also created more negative gravitational energy. The total energy, positive plus negative, remained zero. The universe, in a very real sense, is the ultimate free lunch, a vast cosmos that arose from nothing because its total energy bill is zero. The inflaton field couldn't stay in its false vacuum state forever. Quantum mechanics tells us that systems in false vacuum states will eventually tunnel to lower energy states, like our ball spontaneously appearing at the bottom of the hill. When this happened, when the inflaton field finally rolled down to its true minimum, inflation ended. The energy that had been driving expansion was suddenly released, converting into particles and radiation in a process called reheating. The universe went from being cold and empty except for the inflaton field to being hot and full of matter and radiation. This transition from inflation to the hot Big Bang wasn't instantaneous everywhere. Different regions of space stopped inflating at slightly different times, like different parts of boiling water turning to steam. These tiny differences in timing created tiny differences in density, which were then amplified by gravity over billions of years into the cosmic structures we see today. Every galaxy, every star, every planet owes its existence to these quantum fluctuations in when inflation ended in different regions of space. The speed of this expansion during inflation is almost incomprehensible. Points in space that were initially separated by subatomic distances were pulled apart to distances greater than the observable universe today. And this happened not gradually over billions of years, but in a fraction of a second so small that we need scientific notation to write it down. The expansion was so rapid that regions of space were pulled apart faster than light could travel between them, creating causally disconnected regions that could no longer communicate with each other. This might seem problematic. If different regions of space can't communicate, how did they all end up with the same temperature and density? This is actually the horizon problem that inflation solves. Before inflation, all these regions were close enough together to come to thermal equilibrium. Then inflation pulled them apart faster than light. Preserving that equilibrium even though they could no longer communicate. It's like taking a pot of water that's all the same temperature and instantly expanding it to cosmic size. Different parts can no longer exchange heat, but they're all still the same temperature because they started that way. The quantum nature of the inflaton field adds another layer of fascination to this story. According to quantum mechanics, fields can never be perfectly smooth. They always have tiny fluctuations, tiny ripples that appear and disappear. During inflation, these quantum fluctuations were stretched to macroscopic sizes. A fluctuation that started smaller than a proton was stretched to be larger than a galaxy. These stretched fluctuations became the seeds for all cosmic structure. Think about what this means. The galaxy you live in, the Milky Way, exists because of a quantum fluctuation that occurred during inflation. That fluctuation was stretched from subatomic to cosmic size, created a slight overdensity in matter, and gravity did the rest over billions of years. Every structure in the universe larger than a certain size owes its existence to these primordial quantum fluctuations. We are quite literally living inside enlarged quantum fluctuations. The uniformity of these fluctuations tells us something important about inflation. The fluctuations we observe in the cosmic microwave background are nearly scale invariant, meaning they have roughly the same amplitude regardless of their size. This is exactly what we'd expect if they were produced during inflation, when the expansion rate was nearly constant. It's one of the key pieces of evidence that inflation actually happened. But inflation didn't just stretch quantum fluctuations in the inflaton field, it also stretched fluctuations in space-time itself. These are called gravitational waves, or tensor fluctuations, and they would have left a distinct pattern in the polarization of the cosmic microwave background. Scientists have been searching for this pattern, called B-mode polarization, as it would be a smoking gun for inflation. The fact that we haven't definitively detected it yet tells us that inflation happened at lower energies than some theories predicted, but the search continues with ever more sensitive instruments. The energy scale of inflation is mind-boggling. The temperature equivalent of the inflaton field's energy was about 1016 GeV, which is about 1 trillion times higher than the energies we can achieve in our most powerful particle accelerators. At these energies, the electromagnetic force and the weak nuclear force were unified into a single electro-weak force. The strong nuclear force might have been unified with them as well. We were in a realm of physics that we can describe mathematically but can never recreate in a laboratory. This is one of the most remarkable things about inflation. It gives us a window into physics at energy scales we could never otherwise explore. The patterns in the cosmic microwave background are like fossils from a time when the universe was operating under physical conditions we can only dream of recreating. Every measurement we make of these patterns teaches us something about physics at the highest energies that ever existed. The mechanism of inflation also explains why the universe appears to be so finely tuned for the existence of stars, galaxies, and life. Without inflation, we'd need to assume that the initial conditions of the universe were set with incredible precision, that the density was exactly right, the expansion rate was exactly right, the temperature was uniform to 1 part in 100,000. With inflation, all of these seemingly unlikely conditions emerge naturally. Inflation is an attractor. No matter what the initial conditions were, inflation drives the universe toward flatness, uniformity, and the right conditions for structure formation. Consider the flatness problem in more detail. Einstein's general relativity tells us that space can be curved. It could be positively curved like a sphere, negatively curved like a saddle, or flat like a piece of paper. Observations tell us that our universe is flat to extraordinary precision. Without inflation, this would require the density of the universe 1 second after the Big Bang to be fine-tuned to 1 part in 10^60. That's like balancing a pencil on its point and having it remain balanced for billions of years. But inflation naturally drives the universe toward flatness. No matter what curvature space started with, the enormous expansion of inflation would have stretched it flat, just like inflating a balloon makes its surface appear flatter and flatter to someone standing on it. By the end of inflation, space would be so close to flat that it would remain flat for billions of years, which is exactly what we observe. The same principle applies to magnetic monopoles and other exotic particles that might have been produced in the very early universe. These particles would have been diluted by inflation, to such low densities that we wouldn't expect to see any in our observable universe. This explains why we've never detected magnetic monopoles, even though many theories of particle physics predict they should exist. As we contemplate this mechanism of faster-than-light expansion, it's worth reflecting on what it means for our understanding of reality. Space itself is not a fixed stage on which cosmic events play out. It's a dynamic, flexible, expandable fabric that can stretch and curve and grow. The expansion of space is not something that happens in space. It is something that space does. Space is not just where things happen. It's an active participant in cosmic evolution. This perspective changes how we think about the universe. It's not a container with stuff in it. It's a living, growing, evolving entity where space, time, matter and energy are all interconnected aspects of a single reality. The expansion of space during inflation wasn't something imposed on the universe from outside. It was the universe itself growing, like a living organism developing from a seed. And this growth continues today. Space is still expanding, though much more slowly than during inflation. Galaxies are still moving apart, carried by the expansion of space between them. In fact, observations show that this expansion is accelerating, driven by what we call dark energy. We don't know what dark energy is, but it behaves remarkably like the inflaton field. It has constant energy density even as space expands. Some physicists wonder if we're seeing the beginning of a new phase of inflation that will eventually dilute all matter in the universe to undetectable levels. The possibility that inflation could happen again raises profound questions. If inflation happened once, could it happen multiple times? Could different regions of space undergo inflation at different times, creating a multiverse of pocket universes, each with its own Big Bang, its own laws of physics, its own story? This idea of eternal inflation suggests that our universe might be just one bubble in an infinite foam of inflating space-time. In this view, inflation never completely ends. While it ended in our region of space 13.8 billion years ago, it continues in other regions, constantly creating new universes. Each universe would be causally disconnected from the others, unable to communicate or interact. We could never observe these other universes directly, but their existence would be a natural consequence of the same physics that explains our own universe's beginning. This brings us to one of the deepest questions in cosmology. Why did inflation happen at all? What set the initial conditions that allowed the inflaton field to exist in its false vacuum state? We don't have definitive answers, but we have intriguing possibilities. Perhaps inflation is simply the natural state of empty space at high energies. Perhaps quantum fluctuations occasionally push regions of space into inflating states. Perhaps inflation is eternal and needs no beginning. It has always been happening somewhere. Some theories suggest that inflation arose from a previous universe that collapsed and bounced, with the bounce triggering inflation. Others propose that inflation emerged from the collision of higher dimensional objects called branes in string theory. Still, others suggest that inflation is selected for by anthropic reasoning. Universes that don't undergo inflation don't produce observers to wonder about it. What we do know is that inflation, despite its seemingly impossible faster-than-light expansion, is not only consistent with the laws of physics, but seems to be required by them. The evidence for inflation is written across the sky in the cosmic microwave background, in the distribution of galaxies, in the flatness of space, in the absence of magnetic monopoles. Every observation we make confirms that our universe underwent this period of exponential expansion. As you lie there, perhaps feeling the gentle expansion of your chest as you breathe, you're experiencing a faint echo of that primordial expansion. The space inside your lungs is the same space that expanded during inflation. The air flowing in and out is made of atoms whose constituents were created when inflation ended. The electrical signals in your brain that create your thoughts are governed by the same quantum mechanics that created fluctuations during inflation. You're not separate from this story of expansion. Your expansion temporarily organized into human form. The same process that drove space to expand faster than light drives the gentle expansion of your breathing. The same quantum fluctuations that seeded galaxies create the tiny uncertainties in your neural processes that might be the source of free will. The same vacuum energy that powered inflation might be the dark energy that's accelerating cosmic expansion today. Understanding how space expanded faster than light helps us appreciate the dynamic nature of reality. Nothing is fixed. Nothing is static. Space itself is alive with possibility, capable of dramatic change, able to transcend what seem like absolute limits. The faster-than-light expansion of space during inflation shows us that the universe is far more creative and flexible than our everyday experience suggests. This expansion also connects us to the deepest mysteries of physics. What is space, really? Is it fundamental, or does it emerge from something deeper? Some theories suggest that space and time themselves are emergent properties of more fundamental quantum entanglement. In this view, the expansion of space during inflation would be the emergence of space-time itself from a more primitive quantum state. The holographic principle, inspired by black hole physics, suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. If this is true, then the expansion of space during inflation would be like the unfolding of information from a lower dimensional surface into our three-dimensional reality. We might be living inside a cosmic hologram that was projected during inflation. These ideas might sound like science fiction, but they're serious proposals by respected physicists trying to understand the deepest nature of reality. Inflation opens a window into these fundamental questions because it occurred at energies where quantum mechanics and general relativity both played crucial roles. Understanding inflation might be the key to developing a theory of quantum gravity that unifies our understanding of the very small and the very large. As we prepare to examine the evidence for this faster-than-light expansion, the quiet maps of ancient light that confirm inflation happened, remember that this isn't just abstract physics. This is your story, your history, your cosmic heritage. The faster-than-light expansion of space during inflation is the reason you exist, the reason you can contemplate your existence, the reason the universe is comprehensible at all. The expansion continues in you. Every cell division in your body is a kind of biological inflation, creating more space for life. Every breath expands the space in your lungs. Every heartbeat sends blood expanding through your arteries. You're a continuation of the cosmic expansion that began with inflation, a local organization of that expansion into consciousness and wonder. And perhaps most remarkably, you have the capacity to understand this expansion, to trace it back to its beginning, to comprehend how space itself could expand faster than light without violating any laws of physics. This understanding is itself a kind of expansion, the expansion of knowledge, of awareness, of the universe's ability to comprehend itself. The story of inflation is still being written. New observations might reveal details we haven't imagined. New theories might explain aspects we don't yet understand. But what we know already is profound. The universe began with a moment of impossible expansion that made everything else possible. Space itself stretched faster than light, not violating physical laws but fulfilling them, not destroying possibilities but creating them, not moving through anything but simply becoming more of itself. This is the deep magic at the heart of reality. Space can expand faster than light because space isn't travelling, it's growing. And in that growth, in that impossible possible expansion, lie the seeds of everything that has ever been or ever will be, including this quiet moment where you contemplate the cosmos, and the cosmos contemplates itself through you. The universe has left us a map, a quiet testimony written in the oldest light we can see. This ancient illumination, which scientists call the cosmic microwave background, is like a photograph taken when the universe was only 380,000 years old, a mere infant compared to its current age of 13.8 billion years. But this isn't just any photograph. It's a portrait that carries within its gentle patterns the fingerprints of inflation, the evidence that space really did expand faster than light in that first impossible fraction of a second. Every tiny variation in this ancient light, every subtle difference in temperature across the sky, tells us something about what happened during inflation and how it shaped everything that came after. Imagine standing in a vast, dark room where the walls, ceiling and floor all glow with the faintest possible light. This light is so dim that your eyes could never see it directly, but it's there, filling every cubic centimetre of space around you. It's been travelling since the universe first became transparent to light, carrying information from a time before stars, before galaxies, before any structure existed at all. This is the cosmic microwave background, and it's everywhere. In the room where you're listening to this, in the space between stars, in the vast voids between galaxy clusters. About 400 photons of this ancient light pass through every cubic centimetre of space every second, including the space occupied by your body right now. The discovery of this cosmic background radiation is itself a story of serendipity and scientific beauty. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were trying to use a large horn antenna in New Jersey to study radio waves from our galaxy. But they kept detecting an annoying background noise that they couldn't eliminate. They tried everything, cooling their equipment, removing pigeons that had nested in the antenna, even cleaning out what they delicately called white dielectric material, pigeon droppings, that had accumulated. But the noise persisted, coming equally from all directions in the sky. What Penzias and Wilson had discovered wasn't noise at all. It was the cooled remnant of the Big Bang itself, the afterglow of creation that had been predicted by physicists, but never observed. This radiation had been travelling through space for billions of years, gradually cooling as the universe expanded. What started as blazing hot light had been stretched by the expansion of space into microwave radiation, cooled to just 2.7 degrees above absolute zero. It was like finding the ashes of the primordial fire still warm after all these eons. But the real treasure wasn't just the existence of this background radiation. It was the tiny variations within it. If you could see microwaves and looked at the sky, you wouldn't see a perfectly uniform glow. Instead, you'd see an incredibly subtle pattern of slightly warmer and slightly cooler spots, differences of only about 1 part in 100,000. These minuscule variations are like ripples on an otherwise perfectly calm sea, and they carry within them the story of inflation. You see, when inflation ended and the universe reheated, it didn't happen exactly simultaneously everywhere. Quantum fluctuations in the inflaton field meant that some regions stopped inflating a tiny fraction of a second before or after others. These timing differences created slight variations in density. Some regions ended up with slightly more matter and energy, others with slightly less. These density variations were imprinted on the cosmic microwave background like a fingerprint, and they've been travelling toward us ever since, carrying information about conditions in the universe when it was less than a second old. The first detailed map of these variations came from a satellite called COBE, the Cosmic Background Explorer, launched in 1989. When COBE's data revealed the first clear detection of these temperature fluctuations, the project's lead scientist, George Smoot, famously said it was like looking at God. What he meant was that these tiny variations were the seeds from which all cosmic structure would grow. Every galaxy, every star, every planet owes its existence to these primordial fluctuations that COBE was seeing for the first time. But COBE's vision was blurry, like looking at the sky through frosted glass. The next generation came with WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. WMAP could see details that COBE couldn't resolve, creating a map of the ancient light with unprecedented precision. It was like switching from a standard television to high definition. Suddenly patterns that had been hidden became clear. WMAP's data confirmed many predictions of inflation theory with remarkable accuracy. Then came Planck, a European Space Agency satellite launched in 2009, which pushed our vision of the cosmic microwave background to even greater heights of precision. Planck could measure temperature differences of just a few millionths of a degree, creating the most detailed map of the ancient light that we've ever had. It's like having a photograph of the infant universe, with billions of pixels, each one telling us something about conditions at that cosmic dawn. What do these maps tell us about inflation? First, they confirm that the universe is remarkably flat. If you draw a triangle between 3 distant points in the cosmic microwave background, the angles add up to exactly 180 degrees, just as they would on a flat piece of paper. This flatness is exactly what inflation predicts. The enormous expansion would have stretched out any initial curvature until space became perfectly flat, like inflating a balloon until its surface seems flat to anyone standing on it. The maps also show that the universe is remarkably uniform on large scales. The temperature of the cosmic microwave background is the same, to 1 part in 100,000, whether you look toward the constellation Orion or toward the constellation Scorpius, whether you look toward the North Galactic Pole or the South. This uniformity is the horizon problem that inflation solves. Without inflation, different regions of the sky that we see today would never have been in causal contact, light wouldn't have had time to travel between them. So how could they all have the same temperature? Inflation provides the answer. These regions were in contact before inflation, then were pulled apart faster than light, preserving their common temperature even though they could no longer communicate. But it's the pattern of the tiny fluctuations that provides the most compelling evidence for inflation. These fluctuations have a very specific statistical distribution that matches what inflation predicts. They're nearly scale invariant, meaning the amplitude of fluctuations is almost the same regardless of their size. Large fluctuations and small fluctuations have similar strengths, with just a slight tilt that makes smaller fluctuations slightly stronger. This tilt, called the spectral index, has been measured to be 0.965, with an uncertainty of just 0.004. Inflation predicts a value slightly less than 1, and that's exactly what we observe. Think about what this means. We're measuring tiny temperature differences in light that's been travelling for 13.8 billion years, and these measurements match the predictions of a theory about something that happened in the first 10^32 seconds of cosmic history. It's like finding a message in a bottle that's been floating in the ocean for decades and discovering that it describes, in perfect detail, the moment the bottle was thrown into the water. The cosmic microwave background also tells us about the energy scale of inflation. The amplitude of the temperature fluctuations depends on how high the energy was during inflation. The observed amplitude tells us that the energy scale was about 1016 GeV. That's about 1 trillion times higher than the energies we can achieve in our most powerful particle accelerators. We're using the entire universe as a particle physics experiment, probing energies that we could never recreate on Earth. One of the most exciting searches in cosmology is for a particular pattern in the polarization of the cosmic microwave background called B-modes. Light can be polarized, meaning its electromagnetic waves oscillate in a preferred direction. The cosmic microwave background is slightly polarized, and this polarization can be decomposed into two types of patterns: E-modes, which look like they're flowing out from or into points, and B-modes, which have a swirling chiral pattern. E-modes are produced by density fluctuations and have been clearly detected. But B-modes are special. They can only be produced by gravitational waves, ripples in space-time itself. If inflation happened, it would have produced gravitational waves by stretching quantum fluctuations in the fabric of space-time. These primordial gravitational waves would have left their mark as B-mode polarization in the cosmic microwave background. The search for B-modes is one of the most active areas in cosmology. In 2014, a team using the BICEP 2 telescope at the South Pole announced they had detected B-modes, which would have been direct evidence for inflation. The scientific community was electrified. But further analysis revealed that most or all of the signal was due to dust in our own galaxy, not primordial gravitational waves. The search continues with more sensitive instruments and better ways to separate galactic foregrounds from the primordial signal. The fact that we haven't yet detected primordial B-modes actually tells us something important. It means that the energy scale of inflation was lower than some theories predicted. This rules out some models of inflation and constrains others. Even a non-detection is valuable scientific information when you're probing the first fraction of a second of cosmic history. The maps of ancient light also reveal something called acoustic oscillations. Before the universe became transparent, matter and radiation were tightly coupled, like a single fluid. Sound waves travelled through this fluid, creating a pattern of compressions and rarefactions. When the universe became transparent and the cosmic microwave background was released, these sound waves were frozen in place, creating a characteristic pattern of peaks and valleys in the temperature fluctuations at different angular scales. Imagine dropping a pebble into a still pond. Ripples spread out in circles from the point of impact. Now imagine instantly freezing the entire pond. The ripples would be preserved as a pattern of raised and lowered ice. Something similar happened in the early universe. The pebbles were the quantum fluctuations from inflation. The pond was the plasma of the early universe, and the freezing happened when the universe became transparent. The pattern of ripples we see in the cosmic microwave background tells us about the properties of that primordial fluid and the nature of the initial fluctuations. The spacing of these acoustic peaks tells us about the composition of the universe. The first peak tells us about the total density of matter and energy. The second peak tells us about the density of ordinary matter. The third peak tells us about the density of dark matter. By measuring these peaks precisely, we've determined that ordinary matter makes up only about 5% of the universe, dark matter makes up about 27%, and dark energy makes up the remaining 68%. These percentages are known to remarkable precision thanks to our maps of ancient light. The cosmic microwave background also reveals that the universe is slightly lopsided. There are subtle asymmetries and anomalies that don't quite match what we'd expect from the simplest models of inflation. There's a cold spot that's larger and colder than expected. There's a slight difference in average temperature between two hemispheres of the sky. There are alignments of the larger scale fluctuations that seem to pick out special directions in space. These anomalies might be statistical flukes, or they might be telling us something profound about inflation or about physics beyond our current understanding. One particularly intriguing anomaly is the lack of fluctuations at the very larger scales. It's as if the universe is smoother than expected on scales comparable to the observable universe itself. This might be telling us something about the duration of inflation. Perhaps it lasted just long enough to solve the horizon and flatness problems, but not much longer. Or it might be telling us something about the initial conditions before inflation began. The temperature of the cosmic microwave background also varies slightly depending on our motion through space. Because Earth is orbiting the Sun is orbiting the center of the Milky Way, and the Milky Way is moving through space, we're traveling at about 370 kilometers per second, relative to the cosmic microwave background. This motion creates a dipole pattern. The background appears slightly warmer in the direction we're moving and slightly cooler in the opposite direction. It's like the Doppler effect for light, and it tells us about our motion through the cosmos. When we subtract out this motion, we find that the cosmic microwave background provides a special reference frame for the universe. It's not a preferred frame in the sense of violating relativity. The laws of physics work the same in all reference frames. But it is a natural frame defined by the universe itself, the frame in which the background radiation looks the same in all directions. In a sense, the cosmic microwave background defines what it means to be at rest relative to the universe as a whole. The maps of ancient light also let us test Einstein's general relativity on cosmic scales. As photons from the cosmic microwave background travel toward us, they pass through the gravitational fields of galaxy clusters and cosmic voids. These gravitational fields affect the photons' paths and energies, creating secondary temperature, fluctuations that are superimposed on the primary ones from inflation. By studying these secondary effects, we can map the distribution of matter between us and the surface of last scattering, creating a three-dimensional picture of cosmic structure. One of these effects is called gravitational lensing. Just as a lens bends light, gravity bends the paths of photons from the cosmic microwave background. This creates subtle distortions in the maps, smearing out the temperature fluctuations in characteristic ways. By analysing these distortions, we can determine how much matter the photons pass through on their journey to us. This provides an independent measure of the amount and distribution of dark matter in the universe. Another effect is called the integrated Sachs-Wolfe effect. When a photon enters a gravitational potential well, like the one around a galaxy cluster, it gains energy. When it climbs out, it loses energy. In a static universe, these effects would cancel out. But in our expanding universe, especially with the acceleration caused by dark energy, the potential wells evolve while the photons are traversing them. A photon might enter a deep potential well but exit a shallower one as the universe expands, resulting in a net energy gain or loss. This creates additional temperature fluctuations that tell us about the growth of structure and the effects of dark energy. The Sunyaev-Zeldovich effect occurs when photons from the cosmic microwave background pass through hot gas in galaxy clusters. The high-energy electrons in the gas scatter the photons to higher energies, creating a characteristic distortion in the spectrum of the background radiation. This effect lets us detect galaxy clusters independent of their distance, since the strength of the effect depends only on the properties of the gas, not on how far away it is. It's like having a way to see galaxy clusters silhouetted against the cosmic microwave background. All of these effects layer additional information onto the maps of ancient light. They're like different instruments in a cosmic symphony, each adding their own notes to the primordial melody laid down by inflation. By carefully analysing all of these effects, we can extract an enormous amount of information about the universe's history, composition, and future. The precision of these measurements is staggering. We know the age of the universe to within 20 million years. That's like knowing someone's age to within a few months over an entire human lifetime. We know the Hubble constant, which describes the current expansion rate, to within a few percent. We know the density of ordinary matter, and dark energy to similar precision. All of this from studying the faint glow of ancient light that fills the space around us. But perhaps the most profound thing about the cosmic microwave background is what it tells us about our cosmic horizon. The surface of last scattering, where this ancient light originated, is the most distant thing we can see with electromagnetic radiation. It's our cosmic baby picture, the earliest moment we can observe directly. Beyond it lies the opaque universe of the first 380,000 years, hidden from our telescopes like the interior of the sun is hidden from our view, yet inflation theory lets us peer beyond this veil. The patterns in the cosmic microwave background are telling us about events that occurred when the universe was less than a second old. We're using the visible to learn about the invisible, using the observable to understand the unobservable. It's like being able to determine what happened inside an egg before it hatched by carefully studying the pattern of cracks in the shell. The cosmic microwave background is also our best evidence that the universe really did begin in a hot, dense state. Before its discovery, the Big Bang was just one theory among several. The steady state theory, which proposed that the universe had always existed in roughly its current form, was still viable. But the cosmic microwave background killed the steady state theory. There's no way to explain this uniform background radiation filling all of space except as the cooled remnant of a much hotter, denser past. Every measurement of the cosmic microwave background has confirmed and refined our understanding of inflation. The flatness of space, the uniformity of temperature, the spectrum of fluctuations, the acoustic peaks, all of these features match the predictions of inflation with remarkable precision. Is one of the most successful theories in the history of science, explaining numerous observations with a single elegant idea: that the universe underwent a brief period of exponential expansion, driven by a scalar field, yet mysteries remain. We still don't know what the inflaton field was. Was it a fundamental field, like the electromagnetic field? Was it associated with a particle? And if so, what were that particle's properties? Was it related to the Higgs field that gives particles their mass? Was it connected to grand unification, the hypothetical merging of the fundamental forces at high energies? These questions connect inflation to the deepest mysteries in particle physics. The maps of ancient light might also be telling us about physics beyond inflation. Some theories predict that collisions between bubble universes in an eternal inflation scenario would leave circular patterns in the cosmic microwave background. Others suggest that cosmic strings, hypothetical defects in spacetime, would create characteristic line-like discontinuities. Still others propose that a universe that underwent a bounce before inflation would leave specific signatures. So far, none of these exotic signatures have been definitively detected, but the search continues. As technology improves, our maps of ancient light become ever more detailed. Future missions like CMB-S4, Lightbird, and the Simons Observatory will push our sensitivity to new levels. They might finally detect primordial B modes, providing direct evidence for gravitational waves from inflation. They might reveal new anomalies that point to physics beyond our current understanding. They might confirm or refute specific models of inflation, narrowing down the possibilities for what actually happened in that first fraction of a second. The cosmic microwave background is like a message from the infant universe, written in a language of temperature fluctuations and polarization patterns. We've learned to read this language, to extract from it the story of our cosmic origins. Every photon of this ancient light has been traveling for 13.8 billion years to reach us, carrying information about inflation, about the birth of structure, about the nature of space and time themselves. As you lie there in the darkness, perhaps you can imagine these ancient photons passing through your room, through your body, continuing their billion-year journey. They've travelled from the surface of last scattering, across billions of light-years of expanding space, through galaxy clusters and cosmic voids to arrive here, now, where we've built instruments sensitive enough to detect them and minds clever enough to decode their message. In a very real sense, you're immersed in the afterglow of creation, bathed in light that remembers inflation. This ancient light connects us directly to our cosmic origins. It's not just evidence for inflation, it's a physical link to that primordial moment. The photons detecting by our satellites are the same photons that were released when the universe first became transparent, that carry the imprint of quantum fluctuations stretched by inflation, that remember a time before stars and galaxies existed. When we study the cosmic microwave background, we're not just learning about the past, we're touching it, receiving messages written in light that has been travelling since the dawn of time. Now, as we prepare to explore how those tiny quantum fluctuations became the seeds for all cosmic structure, remember that this isn't just ancient history. The same processes that created fluctuations in the cosmic microwave background are still at work today. Quantum fluctuations are happening right now in every cubic centimetre of space, including the space you occupy. The difference is that today, the universe isn't inflating rapidly enough to stretch these fluctuations to cosmic scales. But in principle, the quantum uncertainty that seeds your thoughts and decisions is the same quantum uncertainty that seeded galaxies and galaxy clusters. The maps of ancient light show us that we live in a quantum universe, where the smallest uncertainties can be amplified to the largest scales, where the microscopic and the cosmic are intimately connected, where the impossible becomes not just possible, but necessary for our existence. These quiet maps, these plots of temperature measured to millionths of a degree, are among humanity's greatest achievements. The decoding of a message sent from the beginning of time, the reading of the universe's birth certificate, the discovery that we are made of amplified quantum fluctuations, stretched to cosmic size by inflation, and then collapse by gravity into the complex structures we see today. In the cosmic microwave background, we see the universe's memory of inflation, preserved in light that has been travelling since before the first stars were born. It's a memory of impossible expansion, of faster-than-light stretching, of quantum uncertainty promoted to cosmic significance. And it's a memory that confirms our theoretical understanding while still holding mysteries, still hiding secrets, still promising discoveries for future generations who will map this ancient light with ever greater precision and perhaps finally detect the gravitational waves that would be the definitive signature of inflation. The stillness of space remembers its violent birth, and that memory is written in the quietest light in the universe, a whisper from the beginning of time that we've only recently learned to hear. Every night as you look up at the darkness between the stars, you're looking through this ancient light, this cosmic memory, this gentle testimony to the impossible expansion that made everything possible. Seeds in the stillness. This phrase captures something profound about how our universe builds complexity from simplicity, how it creates something from what appears to be nothing. During inflation, quantum fluctuations, the smallest possible variations allowed by the uncertainty principle, were occurring constantly in the inflaton field. These fluctuations were smaller than atoms, smaller than protons, smaller than anything we can directly measure. They were mere possibilities, quantum uncertainties that existed for the briefest possible moments before disappearing back into the vacuum. Yet inflation grabbed these ephemeral whispers and stretched them across the cosmos, transforming quantum possibilities into cosmic realities. Imagine a perfectly still pond on a windless morning, so calm that the surface appears like glass. But if you could zoom in with a powerful enough microscope, you'd see that even this apparently perfect stillness is an illusion. At the molecular level, water molecules are constantly in motion, creating tiny ripples that appear and disappear faster than the eye could ever see. Now imagine if, in a fraction of a second, that pond expanded to the size of an ocean, with each molecular ripple stretched to become a wave kilometers wide. This is what inflation did to quantum fluctuations. It took the irreducible uncertainty that exists at the smallest scales and amplified it to cosmic proportions. The quantum nature of these fluctuations is crucial to understanding our universe. According to quantum mechanics, truly, empty space is impossible. Even in the most perfect vacuum, pairs of virtual particles are constantly appearing and disappearing. Fields are fluctuating around their minimum values, and space itself is foaming with quantum uncertainty at the smallest scales. This isn't just theoretical speculation. We can measure the effects of quantum fluctuations in laboratory experiments. The Casimir effect, where two metal plates placed very close together are pushed together by quantum fluctuations, is a direct demonstration that the vacuum is alive with activity. During inflation, the inflaton field was subject to these same quantum fluctuations. At any given point in space, the field's value would fluctuate slightly up or down from its average. Normally, these fluctuations would average out to zero over any reasonable volume. But inflation changed the rules. The exponential expansion meant that regions of space were pulled apart faster than quantum fluctuations could average out. A region that happened to have a slightly higher value of the inflaton field would stop inflating a tiny fraction of a second later than average, ending up with slightly more energy density. A region with a lower value would stop inflating slightly earlier, ending up with slightly less energy density. These differences were incredibly small, variations of only about 1 part in 100,000. If the universe were a vast ocean, these would be ripples only a few millimeters high on waves that are kilometers long. Yet these tiny variations contained the seeds of everything we see in the universe today. They were the cosmic DNA, the blueprint for all future structure, encoded in quantum uncertainty and preserved by inflation. Think about what this means for a moment. Every galaxy you can see in the night sky exists because of a quantum fluctuation that happened when the universe was less than 10^32 seconds old. The Milky Way, our home galaxy, formed from a quantum fluctuation that was originally smaller than a proton, but was stretched by inflation to span millions of light years. The exact position and properties of our galaxy were determined by the random quantum uncertainties that happened to occur in our region of space during inflation. This connects the larger structures in the universe directly to the smaller scales of quantum mechanics. It's as if the universe used a quantum random number generator to determine where galaxies would form, then amplified those random numbers to cosmic scale. The randomness wasn't complete chaos. The fluctuations followed specific statistical patterns determined by the properties of the inflaton field and the dynamics of inflation. But within those patterns, the specific details were truly random, determined by quantum uncertainty rather than any classical cause. The spectrum of these fluctuations tells us about the physics of inflation. In the simplest models of inflation, the fluctuations would be exactly scale invariant, meaning they would have the same amplitude regardless of their size. But quantum effects during inflation create a slight tilt in the spectrum, making smaller fluctuations slightly stronger than larger ones. This tilt, measured to be about 3.5%, is one of the key predictions of inflation that has been confirmed by observations. The quantum fluctuations during inflation weren't limited to the inflaton field. Space-time itself was fluctuating, creating primordial gravitational waves. These are ripples in the fabric of space and time, propagating outward at the speed of the light. Unlike the density fluctuations which needed matter to collapse around them to become visible, gravitational waves from inflation would still be propagating through the universe today, stretching and squeezing space as they pass. The amplitude of these primordial gravitational waves depends on the energy scale of inflation. The higher the energy, the stronger the waves. The fact that we haven't yet detected them tells us that inflation happened at energies below about 10^-16 GeV. This is still enormously high, about 1 trillion times higher than the Large Hadron Collider can achieve, but it's lower than the Planck scale where quantum gravity effects would dominate. This suggests that we can understand inflation using known physics without needing a complete theory of quantum gravity. After inflation ended and the universe reheated, these quantum seeds began their long journey toward becoming the cosmic structures we see today. For the first 380,000 years, matter and radiation were tightly coupled, and the fluctuations oscillated like sound waves in a cosmic symphony. When the universe became transparent and matter was released from radiation, gravity could finally begin its work in earnest. The slightly denser regions had slightly stronger gravitational fields, which attracted more matter, which increased their gravity further, which attracted even more matter. This runaway process, called gravitational instability, slowly amplified the tiny initial fluctuations. But it was a patient process. For millions of years after the universe became transparent, the fluctuations grew slowly, invisibly, in the darkness of the cosmic dark ages. Dark matter played a crucial role in this process. Unlike ordinary matter, dark matter doesn't interact with radiation, so it could begin collapsing under gravity even before the universe became transparent. By the time ordinary matter was released from radiation, dark matter had already formed a cosmic scaffolding of filaments and nodes where the density was slightly higher. Ordinary matter fell into these dark matter structures like water flowing into valleys, accelerating the formation of cosmic structure. The first objects to form from the quantum seeds were probably small dark matter halos, perhaps only a few hundred times the mass of the Sun. These mini halos were too small to form stars. They couldn't trap enough gas to initiate nuclear fusion. But they began merging with each other, growing through hierarchical assembly into larger and larger structures. It's like watching raindrops on a window merge together, with small drops combining to form larger ones, which combine to form even larger ones. When halos reached about 1 million solar masses, they could finally trap enough gas to form the first stars. These weren't like the stars we see today. They formed from pristine hydrogen and helium, without any heavier elements to help cool the gas. As a result, they were massive, perhaps 100 or even 1,000 times the mass of our Sun. They burned bright and hot, living for only a few million years before exploding as supernovae. These first stellar explosions were crucial for the continued growth of structure. They enriched the surrounding gas with heavy elements, making it easier for smaller stars to form. They also provided feedback energy that regulated further star formation, preventing all the gas from collapsing into stars at once. The balance between gravity pulling matter together and feedback pushing it apart shaped how galaxies formed and evolved. As we look at larger scales, we see that the quantum fluctuations created a cosmic web of structure. Galaxies didn't form randomly throughout space, but along filaments and at nodes where multiple filaments intersect. Between these filaments are vast cosmic voids, regions where the initial density was slightly lower and which have become ever emptier as gravity pulled matter toward the denser regions. This cosmic web is one of the most beautiful confirmations of inflation theory. Computer simulations that start with quantum fluctuations matching those observed in the cosmic microwave background and then let gravity act for 13.8 billion years produce a cosmic web that looks remarkably like what we observe. The agreement between theory and observation is stunning. We can predict the statistical properties of galaxy clustering, the abundance of galaxy clusters, the size distribution of cosmic voids, all from the quantum seeds planted during inflation. The exact pattern of the cosmic web in our observable universe is unique, determined by the specific quantum fluctuations that happen to occur in our region during inflation. If we could rerun inflation with different random quantum fluctuations, we'd get a different cosmic web, with galaxies in different places, perhaps including a different Milky Way or no Milky Way at all. Yet the statistical properties would be the same clustering strength, the same void sizes, the same filament properties. It's like shuffling a deck of cards. Each shuffle gives a unique arrangement, but the statistical properties of the deck remain the same. This randomness extends to smaller scales as well. The exact positions of stars within galaxies, the precise orbits of planets around stars, the specific arrangement of atoms in your body, all of these can be traced back in principle to quantum fluctuations during inflation. The universe is deterministic in its laws, but random in its initial conditions, and that randomness was injected during inflation when quantum uncertainty was promoted to classical reality. The growth of structure from quantum seeds also explains why the universe looks the same on large scales, but different on small scales. On scales larger than a few 100 million light-years, the universe is remarkably uniform. Galaxy clusters are distributed roughly evenly, with similar abundances in all directions. This is because the quantum fluctuations were very small, only 1 part in 100,000, so the large-scale universe remained smooth. But on smaller scales, gravity has had time to amplify these fluctuations enormously. A region that was overdense by 0.01% after inflation might be overdense by a factor of 1 million today, having collapsed into a galaxy cluster. The rich structure we see on small scales, galaxies, stars, planets, life, all emerged from tiny quantum seeds through billions of years of gravitational amplification. The process continues today. Galaxies are still merging, clusters are still growing, the cosmic web is still evolving. The quantum seeds planted during inflation haven't finished growing. Our Milky Way will merge with the Andromeda Galaxy in about 4 billion years. Our local group of galaxies will eventually merge into a single giant elliptical galaxy. On the larger scales, the cosmic web will continue to empty its voids and concentrate matter in its filaments and nodes. But this process is fighting against the accelerated expansion caused by dark energy. As the universe expands faster and faster, it becomes harder for gravity to pull matter together. Structure formation is slowing down and will eventually stop. In the far future, perhaps 100 billion years from now, the universe will stop forming new structures. the quantum seeds will have finished their growth, reaching a maximum size determined by the balance between gravity and dark energy. This future limit on structure formation makes our current epoch special. We live in the era when the universe is still actively building complexity from the quantum seeds of inflation. Stars are still forming, galaxies are still merging, new structures are still emerging. We're witnessing the universe in its creative phase, when the seeds planted in the first fraction of a second are still sprouting into new forms. The quantum seeds also determine the abundance of different types of objects in the universe. The number of galaxy clusters of a given mass, the number of galaxies of a given size, the rate at which galaxies merge. All of these depend on the amplitude and spectrum of the initial quantum fluctuations. By measuring these abundances, we can work backward to determine the properties of inflation. One particularly powerful probe is the abundance of galaxy clusters. These are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies. They form only in the highest peaks of the initial density field, where the quantum fluctuations were strongest. The number of clusters of different masses tells us about the amplitude of fluctuations on different scales, providing a direct link to the physics of inflation. Another probe is the clustering of galaxies. Galaxies aren't distributed randomly but show a characteristic pattern of clustering that depends on the initial fluctuations. The probability of finding two galaxies separated by a given distance depends on the spectrum of quantum fluctuations from inflation. By measuring millions of galaxy positions and computing their clustering statistics, we can test inflation theory with remarkable precision. The cosmic web itself is a probe of inflation. The sizes of cosmic voids, the lengths of filaments, the spacing of nodes, all of these features were determined by the quantum fluctuations during inflation. As we map the cosmic web in ever greater detail, we're essentially mapping the quantum fluctuations that were stretched across the sky 13.8 billion years ago. Even the properties of individual galaxies carry information about the quantum seeds. The rotation speeds of spiral galaxies, the velocity dispersions of elliptical galaxies, the distributions of dark matter within galaxies, all of these were influenced by the initial fluctuations. Every galaxy is a fossil record of the quantum seed from which it grew. The connection between quantum fluctuations and cosmic structure has profound philosophical implications. It means that quantum mechanics isn't just relevant for atoms and particles, but determines the large-scale structure of the universe. The uncertainty principle, usually associated with the microscopic world, shaped the distribution of galaxies across billions of light years. Quantum randomness, often thought of as mere noise, became the blueprint for cosmic architecture. This also means that the universe is fundamentally statistical rather than deterministic in its structure. We can predict the probability of finding a galaxy cluster of a given mass, but we can't predict exactly where specific clusters will form. We can calculate the expected properties of the cosmic web, but we can't determine the precise positions of specific filaments and voids. The universe is lawful in its statistics but random in its specifics. The quantum seeds from inflation also connect us to the multiverse concept. If inflation is eternal, creating an infinite number of pocket universes, each would have its own pattern of quantum fluctuations. There would be universes with stronger fluctuations that collapsed into black holes before galaxies could form. There would be universes with weaker fluctuations that never formed any structure at all. Our universe, with fluctuations of just the right amplitude to form galaxies and stars without collapsing into black holes, might be rare or might be typical. We don't yet know. The anthropic principle enters here as well. We necessarily find ourselves in a universe where the quantum fluctuations were appropriate for the formation of galaxies, stars, and planets. If they had been much stronger or much weaker, we wouldn't be here to observe them. This doesn't explain why the fluctuations have the amplitude they do, but it does explain why we observe fluctuations of this particular strength. As we study the quantum seeds in ever greater detail, we're approaching fundamental limits set by cosmic variance. Because we can only observe one universe, we have only one realization of the random quantum fluctuations. On the larger scales, where there are only a few independent fluctuations in our observable universe, we can never measure the statistical properties perfectly. It's like trying to determine if a coin is fair by flipping it only a few times. Random variation limits how well we can measure the underlying probabilities. This cosmic variance is both a limitation and a profound truth. It reminds us that our universe is just one example. one roll of the quantum dice during inflation. The specific pattern of galaxies we see, including our own Milky Way, is contingent rather than necessary. In another realization of inflation, there might be no Milky Way, no solar system, no Earth, yet the laws of physics would be the same, and perhaps other conscious beings in other galaxies would be contemplating their own cosmic origins. The quantum seeds in the stillness also remind us of the deep unity of nature. The same quantum mechanics that describes atoms and molecules also shaped the larger structures in the universe. The uncertainty principle that limits how precisely we can measure a particle's position also determined where galaxies would form. The wave-particle duality that makes electrons sometimes act like waves and sometimes like particles also created waves in the density of matter that became the cosmic web. Every structure in the universe, from the smallest virus to the largest galaxy cluster, owes its existence to quantum fluctuations during inflation. These fluctuations were the universe's first creative act, the injection of information and complexity into what would otherwise be a smooth, featureless cosmos. Without them, the universe would be a uniform sea of particles with no structure, no stars, no planets, no life, no consciousness to contemplate its own existence. As you lie there in the darkness, perhaps you can sense the profound stillness from which everything emerged. The room around you, the building, the planet, the galaxy, all of it grew from quantum seeds that were planted when the universe was younger than the time it takes light to cross a proton. Those seeds waited patiently in the stillness of space, preserved as tiny density variations until gravity could begin its slow work of amplification. You yourself are made of matter that clustered around these quantum seeds. The atoms in your body were pulled together by gravity into the gas cloud that formed our solar system, which itself formed within the spiral arm of a galaxy, which grew from a quantum fluctuation stretched to cosmic size by inflation. Every thought you think occurs in a brain whose atoms were organized by a chain of causation that traces back to quantum uncertainty in the first fraction of a second. This is the deep magic of our universe. It creates complexity from simplicity, structure from randomness, consciousness from quantum uncertainty. The seeds in the stillness weren't just the beginning of cosmic structure, they were the beginning of possibility itself, the first notes in a symphony that's still playing, still evolving, still creating new harmonies from those primordial quantum whispers. The stillness continues. Even now, quantum fluctuations are occurring in every cubic centimeter of space. Virtual particles appear and disappear. Fields fluctuate around their minimum values. Space itself foams with quantum uncertainty at the smallest scales. These modern fluctuations are too small to seed new cosmic structures. The universe is no longer inflating rapidly enough to stretch them to cosmic size. But they're the same type of fluctuations that seeded everything we see. Reminders that the quantum realm remains active, creative, full of potential. In the far future, when the universe has expanded and cooled to near absolute zero, quantum fluctuations will be the only activity remaining. Even in the heat death of the universe, the quantum seeds will continue their eternal dance, creating virtual particles, temporary variations, fleeting possibilities in the cosmic stillness. The universe began with quantum fluctuations and will end with them, the alpha and omega of cosmic creativity. Now, as we prepare to explore the alternative theories and ideas about the dawn of the universe, remember that all of them must explain how quantum seeds became cosmic structures. Any alternative to inflation must account for the tiny variations we observe in the cosmic microwave background, the spectrum of these fluctuations, their nearly scale-invariant nature, and how they grew into the cosmic web we see today. The seeds in the stillness are facts that any theory must explain, quantum whispers that became cosmic shouts, uncertainty that became structure, possibility that became reality. The universe found a way to build everything from almost nothing, to create complexity from quantum simplicity, to grow forests of galaxies from seeds smaller than atoms. This is perhaps the most profound discovery in cosmology, that everything we see emerged from quantum uncertainty stretched to cosmic scales by inflation, seeds in the stillness that grew into the magnificent universe we inhabit today. Other dawn stories. This acknowledgement of alternative possibilities reminds us that science is not dogma, but an ongoing search for truth, always open to new ideas, always willing to revise its understanding when presented with better explanations. While inflation has become the leading theory for the universe's beginning, earning its place through successful predictions and elegant solutions to cosmic puzzles, it is not the only story that scientists have told about the dawn of time. These alternative narratives, each with its own beauty and challenges, help us understand inflation better by showing us what else is possible, what other paths the universe might have taken to arrive at the cosmos we observe today. Before inflation became the dominant paradigm, cosmologists wrestled with other solutions to the horizon and flatness problems. Some of these alternatives have faded into obscurity, unable to match inflation's explanatory power. Others have evolved and adapted, incorporating aspects of inflation while proposing different mechanisms or interpretations. Still, others persist as radical alternatives, challenging us to think beyond the inflationary paradigm entirely. Each of these dawn stories offers its own perspective on how the universe could have begun, its own answer to why space is flat, why the cosmic microwave background is uniform, and how quantum fluctuations became cosmic structures. One of the most enduring alternatives is the cyclic or ekpyrotic universe. In this scenario, our Big Bang was not the beginning of everything, but merely the latest in an eternal sequence of cosmic cycles. The universe expands, eventually contracts, and then bounces, beginning a new cycle of expansion. The bounce itself, rather than inflation, solves the horizon and flatness problems. During the contraction phase, different regions of space have time to come into causal contact and equilibrate. The bounce naturally drives the universe toward flatness, like repeatedly stretching and releasing a rubber sheet tends to flatten out any wrinkles. The ekpyrotic model, whose name comes from the ancient Stoic idea of cosmic fire, proposes that our universe collided with another three-dimensional universe moving through a higher dimensional space. This collision generated the heat and matter we associate with the Big Bang. In this picture, what we call the Big Bang was actually a big splat, the moment when two universes collided along a hidden extra dimension. The collision would naturally create a hot, dense, nearly uniform universe without needing inflation. These cyclic models have a poetic appeal. They suggest that the universe is eternal, without beginning or end, constantly renewing itself like a phoenix rising from its own ashes. They avoid the philosophical puzzles of creation from nothing, replacing them with eternal cycles of death and rebirth. Each cycle might last trillions of years, with our current expansion eventually reversing and leading to another bounce, another Big Bang, another universe full of possibilities. But cyclic models face significant challenges. The second law of thermodynamics tells us that entropy always increases, so each cycle should be more disordered than the last. After many cycles, the universe should be in a state of maximum entropy. Yet we observe a universe far from equilibrium. Some cyclic models try to solve this by having the universe grow larger with each cycle, providing more room for entropy, but this leads to other problems and begins to look suspiciously like inflation in disguise. The bounce itself is problematic in general relativity. When matter becomes dense enough, it forms black holes from which nothing can escape. A contracting universe should collapse into a black hole rather than bouncing. Cyclic models need new physics at high densities to prevent this collapse, often invoking quantum gravity effects that we don't yet understand. Some versions use string theory or loop quantum gravity to create a bounce, but these remain speculative ideas without experimental confirmation. Another alternative is the string gas cosmology, which emerges from string theory's suggestion that the fundamental constituents of nature are not point particles, but tiny vibrating strings. In the very early universe, these strings would form a hot gas, with strings wrapping around the compact extra dimensions that string theory requires. As the universe evolved, the wrapped strings would prevent some dimensions from expanding while allowing our three spatial dimensions to grow large. In this picture, the universe begins in a state of maximum symmetry, with all dimensions roughly the same size. The string gas naturally drives the universe toward three large spatial dimensions because strings can most efficiently collide and annihilate in 3 dimensions. The wrapping and unwrapping of strings around extra dimensions provides a mechanism for smoothing out inhomogeneities and creating the uniform universe we observe, potentially without needing inflation. String gas cosmology offers intriguing connections to fundamental physics. It suggests that the number of large spatial dimensions we observe, 3, is not arbitrary but selected by string dynamics. It provides a role for the extra dimensions that string theory requires, but that we don't observe, and it connects cosmology directly to the microscopic physics of strings, suggesting that the largest and smallest scales are intimately related. Yet string gas cosmology struggles to match inflation's quantitative successes. It has difficulty producing the nearly scale-invariant spectrum of fluctuations we observe in the cosmic microwave background. The detailed predictions depend on aspects of string theory that we don't fully understand, making it hard to test the model against observations. And like many alternatives to inflation, it requires new physics that hasn't been confirmed experimentally. The varying speed of light, VSL theories, propose a radical solution. Perhaps the speed of light was much higher in the early universe. If light could travel faster, then regions of the universe that seem causally disconnected today could have been in contact, solving the horizon problem without inflation. As the universe cooled, the speed of light would have decreased to its current value, freezing in the uniformity established when communication was possible. This idea challenges one of the pillars of modern physics, the constancy of the speed of light. But its proponents argue that only the dimensionless constants of nature, ratios like the fine structure constant, need to be truly constant. The speed of light itself could vary as long as other constants varied in concert to keep dimensionless ratios fixed. In some versions, what varies is not the speed of light per se, but the speed of gravity or the rate of cosmic expansion, achieving similar effects. VSL theories can solve the horizon problem and, in some versions, the flatness problem as well. They can produce density fluctuations through mechanisms different from inflation, though matching the observed spectrum is challenging. They make some unique predictions, such as specific patterns in the cosmic microwave background that differ subtly from inflation's predictions. As our observations become more precise, we may be able to distinguish between VSL and inflation. But VSL theories face theoretical hurdles. Varying fundamental constants raises questions about energy conservation and the consistency of physical laws. The mechanism that would cause the speed of light to vary and then stop varying at just the right value is unclear. And like other alternatives, VSL theories lack the elegance and predictive power that have made inflation so successful. Another class of alternatives involves modifying gravity itself. Perhaps Einstein's general relativity, successful as it has been, needs modification at the extreme energies of the early universe. Theories like loop quantum cosmology suggest that quantum effects create a repulsive force at very high densities, causing a bounce instead of a singularity. Other modifications add extra terms to Einstein's equations that become important only at high energies, potentially driving a period of rapid expansion without an inflaton field. These modified gravity theories often emerge from attempts to quantize gravity. Loop quantum gravity, for instance, suggests that space itself is quantized at the smallest scales, made of discrete units rather than being continuous. When the universe is compressed to near the Planck density, these quantum effects would prevent further compression and cause a bounce. The pre-bounce universe would have had time to equilibrate, solving the horizon problem, and the bounce would drive the universe toward flatness. Some modified gravity theories predict signatures that could distinguish them from inflation. They might produce a different pattern of gravitational waves or create non-Gaussianities in the cosmic microwave background that inflation wouldn't generate. As our observations become more sophisticated, we may be able to test these predictions and potentially rule out or confirm alternatives to inflation. The matter bounce scenario proposes that the universe underwent a period of contraction dominated by matter before bouncing and expanding. During the contraction phase, quantum fluctuations would be amplified differently than during inflation, potentially producing the observed spectrum of density perturbations. The bounce itself would solve the horizon and flatness problems, while the matter-dominated contraction would seed structure formation. This scenario requires a mechanism to create the bounce, often invoking new physics beyond general relativity. It also needs to explain how the universe transitioned from contraction to expansion, without creating unwanted artifacts in the cosmic microwave background. Recent work has shown that matter bounce scenarios can match many of inflation's successes, though they generally require more complex physics and fine-tuning. Some physicists have proposed that the universe emerged from a quantum tunneling event, spontaneously appearing from nothing through quantum fluctuations. In this picture, the universe is a quantum fluctuation that grew large, like a virtual particle that borrowed energy from the vacuum and never gave it back. The laws of quantum mechanics would select for universes that can grow large and last long, naturally producing something like our observed cosmos. This quantum creation scenario sidesteps the question of what came before the Big Bang by suggesting that time itself began with the quantum tunneling event. There was no before, because time didn't exist. The universe appeared with space, time, matter and energy all emerging together from the quantum vacuum. The probability of different universes appearing would be determined by their quantum wave functions, with our universe being one of the more probable outcomes. The holographic cosmology takes inspiration from the holographic principle in black hole physics. It suggests that our three-dimensional universe is actually a projection from information encoded on a two-dimensional surface, like a hologram. The early universe would be described not by three-dimensional physics, but by a two-dimensional theory on its boundary. What we perceive as cosmic evolution, including inflation or its alternatives, would be the three-dimensional manifestation of two-dimensional dynamics. This radical reimagining of cosmology could potentially solve the horizon and flatness problems in novel ways. The two-dimensional theory might naturally produce the uniformity and flatness we observe when projected into three dimensions. It might also generate the spectrum of fluctuations we see, though through mechanisms completely different from inflation. The holographic perspective suggests that our usual ways of thinking about space and time might be approximations of something more fundamental. Each of these alternative dawn stories reminds us that inflation, successful as it has been, is not the only possibility. Science progresses not by accepting a single theory as dogma, but by constantly testing, questioning, and exploring alternatives. Even if inflation is correct, understanding why other theories fail helps us better appreciate what makes inflation work. And if observations eventually contradict inflation's predictions, these alternatives provide other paths to explore. The diversity of dawn stories also highlights what any successful theory must explain: the uniformity of the cosmic microwave background, the flatness of space, the spectrum of density fluctuations, the absence of magnetic monopoles. These are facts that any theory must account for. Inflation provides elegant explanations for all of these, which is why it has become the leading theory. But the alternatives show that there might be other ways to achieve the same results, other mechanisms that could produce the universe we observe. Some physicists argue for a synthesis, combining elements of different theories. Perhaps there was a bounce or a cyclic phase before inflation. Perhaps inflation was driven not by a scalar field but by modified gravity or extra dimensions. Perhaps the holographic principle provides a deeper understanding of what inflation really was. These hybrid models try to combine the successes of inflation with insights from alternatives, creating richer, more complete pictures of the early universe. The philosophical implications of these different dawn stories are profound. If the universe is cyclic, then our Big Bang was not unique, and there might be infinite cycles stretching into the past and future. If the universe emerged from quantum tunneling, then it truly came from nothing, requiring us to rethink causation and existence. If we live in a holographic universe, then our three-dimensional reality is a kind of illusion, a projection from a more fundamental two-dimensional reality. Each dawn story also makes different predictions about the ultimate fate of the universe. Inflation suggests continued expansion, an eventual heat death. Cyclic models predict an eventual contraction and bounce. Some quantum creation scenarios suggest the universe could tunnel back into non-existence. The holographic models might imply fates we haven't even imagined yet. Our observations of the early universe thus connect directly to questions about cosmic destiny. The search for evidence distinguishing between these dawn stories drives much of modern cosmology. Every new observation of the cosmic microwave background, every survey of galaxy clustering, every detection of gravitational waves provides data that could support or contradict different theories. We're like detectives gathering clues about a crime that happened 13.8 billion years ago, trying to reconstruct what happened from the evidence left behind. Future observations may finally distinguish between inflation and its alternatives. The detection of primordial gravitational waves would strongly support inflation while challenging most alternatives. Specific patterns of non-Gaussianity in the cosmic microwave background could favor certain models over others. Observations of the universe on the very largest scales might reveal signatures of a pre-inflationary phase, or suggest that our universe is part of a larger multiverse. But perhaps the most important aspect of these alternative dawn stories is that they keep us humble. They remind us that our understanding of the universe's beginning is still incomplete, that there are mysteries we haven't solved, questions we haven't answered. They prevent us from becoming too attached to any single theory, too confident in our current understanding. They keep cosmology alive as a science, constantly questioning, constantly exploring, constantly seeking deeper truths. As you contemplate these different possibilities for how the universe began, remember that you're participating in one of humanity's oldest activities, wondering about origins. Every culture has its creation myths, its stories about how everything began. Modern cosmology is our culture's attempt to answer these ancient questions using observation, mathematics, and physical law rather than mythology and revelation. Yet the sense of wonder remains the same. Whether the universe began with inflation, a bounce, a collision, or quantum tunneling, the result is the cosmos we inhabit, vast, beautiful, complex, and comprehensible. Each dawn's story is an attempt to explain how this magnificence arose from simplicity, how the void gave birth to being, how nothing became everything. The fact that we can even contemplate these possibilities, that we can gather evidence and test theories about events that happened billions of years before Earth existed, is itself a kind of miracle. The diversity of dawn stories also reflects the creativity of human thought. Faced with the mystery of cosmic origins, physicists have imagined scenarios that would seem like pure fantasy if they weren't grounded in mathematics and observation. Colliding universes, varying constants, quantum tunneling from nothing, holographic projections. These ideas push the boundaries of imagination while remaining tethered to scientific rigor. In the end, the universe's actual dawn story might be stranger than any we've yet imagined. It might combine elements from multiple theories in ways we haven't anticipated. It might involve physics we haven't discovered, mathematics we haven't invented, concepts we haven't conceived. The dawn of the universe might be so alien to our everyday experience that our current theories, including inflation, are just approximations, shadows on the wall of Plato's cave. Yet we continue searching, continue proposing new dawn stories and testing them against observation. Each alternative we explore, whether it succeeds or fails, teaches us something about the universe and about the boundaries of physical law. Each dawn story we tell reflects not just our understanding of the cosmos, but our aspirations to understand, our refusal to accept mystery without investigation, our determination to trace effects back to causes no matter how far back that trail leads. The alternative dawn stories remind us that inflation, for all its successes, is not the end of cosmology, but a chapter in an ongoing investigation. Future generations may look back on our current understanding the way we look back on earlier cosmologies, as steps toward truth rather than final answers. They may discover that inflation was essentially correct, or that it was a useful approximation of something deeper, or that it was entirely wrong, and the universe began in some way we haven't yet imagined. This uncertainty is not a weakness of science, but its strength. It means cosmology remains open to new ideas, new observations, new revelations. It means the story of the universe's dawn is still being written, still capable of surprising us. It means that anyone, perhaps even you listening to these words, might contribute to our understanding of how everything began. As we prepare to explore the ongoing search for evidence of these cosmic beginnings, for the whispers of primordial gravitational waves that could confirm or refute our theories, carry with you this sense of open possibility. The universe might have begun with inflation, or with a bounce, or with something we haven't imagined. But whatever the true dawn story, it produced a cosmos capable of contemplating its own origins, of telling stories about its birth, of searching for truth in the faint whispers of ancient light.